Now, two blue bars on, okay? Just keep a check sometimes. So, our first chapter in chemistry, this chapter will be taught in grade 9. This won't be taught in grade 10. Acha, how many of you today had a chat with your teacher? What is the course, ma'am, for grade 9 and 10? How many remembered and how many forgot? She didn't go to school. Yes, Nidhi madam, apart from the whole gossip and the fun that you did in school, did you remember this question that you had to ask? Forgot. Oh, I got my answer. I got my answer. No, whether you get your book or not, okay. This chapter anyway will be in grade 9. This won't be in grade 10. Okay. So our first chapter will be states of matter. There might be certain changes from book to book in terms of the name of the chapter, but overall the contents don't change, whether you are studying it in Cambridge, you study in CBSE or anything else. Okay, states of matter. Pay utmost attention, and finer points I'll tell you that you note this in red color. This will be required. Okay, we'll go by some basic before we get into the book. Let's say we have something called matter. This is something that we have been learning from grade 6 onwards. So some of the key aspects when we come to describe matter, we say matter is anything that has mass. Okay. Then we say occupies space. Matter occupies space. That means some volume it will occupy. Right? Look at my marker pen. It is matter. So it has got mass. And it also occupies some space. If I keep it on my palm, this portion of my palm, it is occupied. Now, there is one more attribute which I add, because if I think about something like air, is air matter? Yes, air is also matter. But your heart doesn't immediately agree. Air has mass. But since you can't see it, these two attributes are difficult for you to somewhat accept, okay? But they are truth. So for air and things that we cannot see are still matter, we say can be felt. This completes the definition. Matter has mass, matter occupies space, and matter can be felt. Do you feel it? The fan is right now switched on and it is blowing air in the room, and you can feel it. Even if you close your eyes, you can say that the fan is blowing on because the air is felt on your skin. Are we fine? Okay. This is. So, in the universe, everything in the universe is comprising of matter. So, as chemists or students of chemistry, our intention is to study matter. What is matter made of? What are the properties of matter? So when we study matter, we study it under two specific heads, okay? We can have a chemical classification of matter, chemical classification, and we can also have something which is known as a physical classification. Nidhi, are the letters legible to you? I saw them on large television at my home. They are quite legible. There should not be. Did you play the video back? Just whether there may not be any voice on that, but it's legible on the video. And don't try to see the videos on mobiles. They actually will kill your interest. Always see them on at least a computational device or a television screen. Okay. When you bring a chemical composition of classification of matter, you will be landing up classifying matter as elements, compounds, and mixtures. This is your golden chance to actually clarify all your doubts that have been prevailing in your mind over the years. What is element, what is compound, and what is mixture? We will study this part also in this chapter, and we shall be also studying the physical one. The physical one means matter can be grouped as solid, liquid, as well as gas. Is this much understood? So in physics, we say we have three states of matter. Now there are four states of matter. People call plasma also as one state of matter. But these are the prime three states of matter which we will be studying and are generally studied at school and college level. Okay? So first we will be studying this part, solid, liquid and gas. So let's see some illustrations. Let's see some illustrations. This is something which is taught in CBSE nicely. We can also have a look at it. Some illustrations which will give us some knowledge about matter. So the illustration is something like, let me say that there is a beaker, and this beaker contains water in it, clear water in it, okay, clear water. And there is a crystal of a chemical called potassium permanganate. This is potassium permanganate. You should know these also. This is a very common reagent in lab, KMnO4. If you have gone any of your, like, not Pebble City, if you have gone to your own native place houses which have got, independent house, and you have a water which is being pulled out by a pump, and you have your own tank which is right below the ground, you will find that your relatives are pouring potassium permanganate on it. This works like a disinfectant also. It's absolutely purple, somewhat much more darker than the t-shirt that he is wearing. It will be purple in color as a crystal. So as soon as you drop a crystal of potassium permanganate, what you observe here is that the same beaker, this is the same beaker, okay, the same beaker now gets a uniform purple color of potassium permanganate. Have you understood? The entire color became, this was pink crystal, and the pink crystal started to dissolve. So I write that this potassium permanganate crystal, there was a crystal, and this crystal started to dissolve. This started to dissolve, and then this particular item spread evenly, and so the color changed. Have you understood this? Right? No issues. Now what I do, I again get a similar beaker, and now this was my first beaker. This is the first beaker, A and A. Have you understood? These are the same beakers. This was when I dropped the crystal, and this is after I dropped the crystal. What is the observation that I'm finding in it? Now I take a beaker B. This is my beaker B, and I bring crystal water, clear water in it again, clear water. Now what I do, with the help of a dropper, I take out one drop of potassium permanganate solution from here, okay, and I put that drop out here. Yeah. Well, the funny thing that we will see is, or the interesting thing we'll see, this is again beaker B. Again, the entire water has become pink. And no matter we go on repeating over beaker and beaker, so here I say potassium permanganate crystal, it dissolved. It dissolved and spread evenly. Here the drop or the droplet dissolved and spread evenly. Have you understood this part? Now let us put some analogy to it. Think about a playground, a large playground, where there are some students of your school who are dressed in complete white uniform, and they're standing at some space in between them. But there are a lot of students, say 200 students of white uniform. And then suddenly we open a gate and we allow 200 students wearing red uniform go and mix within them. They go and they mix, and say we make it 200, 300 red uniform guys. Slowly, and I'm watching from an aeroplane right from top. What do I see? The entire white patch now starts getting red. Try to put the same analogy out here. Something that should strike in your mind, what was in this crystal that spread here? There has to be something. Our naked eye are not able to see those students out here, the red color uniform students, but something must have ran and spread across here. Are you understanding that part? So this illustration makes us conclude that matter is composed of particles. Later on, these are the particles which we will be talking a lot about in terms of atoms and compounds, okay? Sorry, atoms and molecules, but matter is composed of particles. Now tell me, Sahasra, did you with your naked eye see any particles running across? No. But after some time you saw that the entire water became. So same thing which you can do at your home. Suppose you take a glass of milk at normal temperature and you pour 2-3 drops of strawberry or any essence into it. First you will see the drop going inside, then you will see some fume like things, and after some time you see the entire milk has become pale pink or something. So I will try to put an adjective out here. Matter is composed of tiny particles. Does that make sense? The particles are tiny. And what are these particles? We right now don't know. But we know that matter is composed of particles. Is this illustration understood by you? Very good. Any question here so far? No. Okay. So can I rub this portion, children? Whenever I'm rubbing something, I'll ask you and you do let me know. Okay. Let's see another illustration. Another illustration. And this is exactly for me, it's like back to back same class. I thought the same thing to CBSE 9 just before you came. Same thing. Okay. So let's say there's a lovely cup of, and again clear water in this cup, and we are like high-end people. We don't take sugar in teaspoon. How many cubes of sugar would you like to take? 2 cubes. You understand? They say sugar cubes, all of you must have seen. So 2 cubes of sugar. I have made them. Hey Nidhi, are you able to see everything and hear everything properly? Okay. So 2 cubes of sugar. What will be your observation? I just took 2 cubes of sugar and I poured on my cup of water at normal temperature. What is your observation? Sugar cube is white in color. Water is also clear color. So what is the observation? What do you think? Cambridge is all about answering and thinking.
Water is slightly.
He said no, but what is the like? Okay, you know the story, like in Mahabharata they say everyone was asked what is this, somebody says it's the bird, somebody says fruit, but Arjun says I see the eye of the bird. So your answering should be like that. What is the answer? What is the observation that will be striking that will happen? The sugar dissolves. The sugar dissolves. See, try to link. If from this example I am going into this example, the storyline cannot change. So I say that the sugar dissolves. But however, out here, like we saw a color phenomenon, we don't see a color phenomenon out here. So this particular illustration also tells me, so I would say that the sugar particles, I say sugar particles dissolved and got spread in water. Do you agree? Got spread in water. So far, our mindset becomes as such that only KMNO4 is matter and sugar is matter. Is water not matter? Water is also matter. And if water is matter, it should also have particles. And don't you think the particles of water had sufficient atithi devo bhava and welcoming attitude that they welcome the particles of sugar? So some scenario like this must have happened. These are the particles of water. Agree? Let's say water particle, water particle, water particle, and water particle. And let's say the sugar particles are smaller in size. So the sugar particles came and said, hey, water, how are you? Oh, long time, we didn't meet. We have not seen each other. And they have evenly spread. This is what is happening. Has to happen. That means, if you go back to that ground example of the school, I first made you stand at a space between each other. Otherwise, how will the red children come and get in? If you guys in the white uniform were exactly body to body touch together, then the red children cannot come and get in. So this makes us another conclusion that matter is composed of tiny particles, and I would say that matter particles have spaces between them. Tell me, children, do you agree with me or not? They have spaces between them, right? Now some more interesting observation. Sahasra starts getting mischievous and she says, sir, let's do one thing, let's pour 16 cubes of sugar into it. So we see after some time 16 cubes also dissolved. Then her mischievous mind says, sir, let me take 32 more cubes and drop out here, and she drops 32 more cubes. After that, what will you see? Some of them won't dissolve. Space full. How do you make it dissolve? You heat, you add more water. Okay, let me give you one more example. When you come by an aircraft, say generally an Indigo aircraft or something has come, you generally see a shuttle which has come to pick you up from the aircraft. And when the shuttle just comes, you will first find the tendency of the human beings to go and all stand near the door. And there will be many people who are thinking to alight in the shuttle, but they feel there is no space inside, as if they're all VIPs and fresh shuttles will be coming. Then comes the indigo person in blue shirt. Ma'am, please get inside. Please get inside. Please get in. Please get in. He's doing something, and immediately those people inside the bus spread across, and more people are about to get in. And then after some time, no more people can get in. He locks the bus and just does and tells the driver to go before the next shuttle comes in. Our condition right now is that whenever you find that a solution is no more able to take any more addition to it, we say that the solution is saturated. Right? If I say you guys just came at 7 o'clock to my house, you are now empty mind. You are ready to take all the gyan that I'll give you. But if I go on teaching you chemistry till 12 o'clock, you will get saturated. Everything will pour out. But my condition is this girl mischievously made it a saturated cup of sugar solution. I now want to add more sugar to it. So whenever we talk about saturation, please remember, these may be linked with this chapter or not. Keep your eyes and ears open. Saturation is always with a particular temperature. Understand? If I take this cup of sugar solution and put it into a microwave oven now and I start heating it, you are giving energy to it in the form of heat. As soon as you give energy, these particles start dancing and they create more spaces. Sugar come up, sugar come up, and they come up. And the first thing before going into the microwave, what will you do? You will take a spoon and you will need to stir it. By stirring, what are you doing? There's something you learned in physics. When body and body rubs against each other, friction. You're causing friction. Friction generates heat, energy. Less as compared to the microwave, but substantial for it to get dissolved. Yes or no? After giving heat and all, still I want more should get in. Now what has happened? The indigo guy has come and he has said, hey, get inside, get inside. This is like giving heat. And if it was our days bus conductor, when we used to go to school, our bus conductors were not so loving like they do to you. Our bus conductor, hey, and immediately they used to scold us and we used to get inside. And all could see it. And the moment the bus conductor used to turn aside, we used to push those little kids, hey, you go and sit, this is my seat. That's nature's law. Okay, so after you have given heat and all, you made it full saturated now and you have closed the indigo bus. You still want more passengers to get inside. You still want more sugar to get in. Now what do? What is the option? You want more people still to get inside the indigo bus. What is the option? Cut open the bus and increase the bus's size. Add more water to this solution. Increase the volume. Again, new water particles. Hey, come, darling, there's more seat here. So you understand? Solubility can be impacted either by temperature. This is something we may read later on also, but your brain should start absorbing. Solubility can be impacted by temperature, can be impacted by pressure also, and can also be impacted by dilution. If you dilute, you allow more of particles to get inside. Are you understanding? Okay, let me give you one more example. All of you must have sometime felt ill, viral fever and stomach upset and all. You are given one pack of thing called ORS, oral rehydration salts or solution, which you actually pour into water and you are supposed to drink that water. That will rehydrate you. Got it? Everyone must have done that. So there must be one sachet of ORS in your home right now also. They are available in orange flavor and our citrus flavor. Now, suppose this bottle of water. Now, this bottle of water is water at normal temperature. The ORS is manufactured in such a way that even if you start dropping ORS out here, it will immediately dissolve. And she is supposed to drink it. Basically, she is drinking a solution of sugar and salt to rehydrate herself. What if I bring chilled water from the refrigerator and pour a sachet of ORS powder into it? What is the difference I'll observe? It will not dissolve. Sachet. Because it's cold. Cold means the temperature is less. You have taken out the energy. So these water molecules are So this fellow comes and says, can I have some space in between? God, no space. Or else, let us mix ORS in her bottle right now and let's refrigerate this bottle. What will you observe? No. I'm saying, I mix ORS in this bottle. It will immediately get dissolved and I just chill it for some time. What is the observation I'll see?
The water particles and essentially mixed in all the fluids.
No, you'll see the ORS particles again coming out. They'll come out. You can do it at your home. These are, see, if you want to love chemistry, chemistry gets boring for people. Why? Chemistry is the literature of science. There's a lot of theory, but it's very fun. And your kitchen is your first lab. Lot of things you'll get in your kitchen. You'll have acid, you'll have base, everything. What I say, sometimes when you're going to MedPlus, one ORS will cost you hardly 10 rupees. Bring that ORS, mix it. Anyway, it will rehydrate you. Sir said after mixing, you need not mix it also, it will readily mix up. Just put that ORS bottle into refrigerator for say half an hour or 30-40 minutes. Not deep freeze, just chill it. And you'll see whatever got mixed, they'll all settle out here in the bottom. Why? Because these particles kicked out the other particles. So matter has space in between them. This is what we learned. Matter has spaces in between them. Are these two properties, children, clear to you? One is matter is composed of tiny particles. And because why I am stressing on this, when we start reading the next section of this particular unit, which will be kinetic theory of matter, at that time these will come into picture. So rather than encountering it there, let us encounter it from right now itself. Matter is composed of tiny particles, and these particles of matter have spaces in between them. Understood? Let's see one more illustration, and that would be our third illustration. And that illustration is something like, let's say we take a stagnant puddle of water. This is a stagnant puddle, okay? This is a stagnant puddle of water. Understood? You know what are pollens? Flower, jasmine flower, you have seen the stigma comes out and you've got a lot of pollens. Earlier in childhood days, we used to just thrash it on somebody's shirt and it sticks into so small. The idea is pollens are, in all these examples, we have been talking about particles, but the particles are not visible to our naked eye. So let's now see some visibility aspect also. So we have taken pollens. Pollens are extremely tiny but are colored, so they are visible to us. Do you agree? So let's take some pollens and drop those pollens out here. Pollen 1, pollen 2, pollen 3, all these are pollens, okay? These are pollens in a puddle of water. Observation that you will be getting out here is that if you pick up one pollen, you will suddenly see it going here, then going this way, then going this way, this way, this way, this way. There is no random motion this pollen will be moving around. It happens. This motion is something called a zigzag or a random motion. If you are unable to relate to this zigzag or random motion, all of you must have gone to a movie theater. So whenever the projector beam is beaming from the projector to the screen, you look at the beam, there will be a lot of dust particles, and you look at the particles, they are just random motion. Or say, suppose, very apt example for you all, on a cold morning you all are sleeping and somebody in your room has come and just pushed aside the curtain and the first light comes in, so you see some dust particles also. So you'll see those dust particles in random motion. This motion was actually discovered by a person called Robert Brown. So it is named in his, whether in your syllabus or not, know it. This is known as Brownian motion. Brownian motion. Brownian motion is a zigzag motion or random motion. If Sahasra would have discovered this, it would have been known as Sahasrian motion. Just because Robert, nothing great. He just saw one motion and named it as Brownian motion, right? Question now arises, why is this particle going in random motion? This is not flowing water. This is stagnant water. What is causing these particles to move across? So let us take one more illustration. Say suppose we are in a football field and the match has not yet started and the team is practicing. They have a soccer ball and they just dribble the soccer ball. Somebody is hitting it from here to here. No random. It's a random dribbling going on. You're not playing a match. Now compare yourself, this example, to what I said right now. Okay, participate in the discussion. Make the football as your pollen. So some football players are there who are kicking that particular football. Out here, like the football was moving randomly from this corner to this corner, and you just, from your mind, you just take away those players and concentrate on the football from a building top. What do you see? The football is going this way, that way, random. Then you try to think, why is the football going random? Oh, as if you have come from some other planet. Oh, this man, when he kicks, he is kicking, and they're kicking in random motion. Now bring the football concept to this. The football is the pollen. Who is the player? the water particles. Now our concentration is on the water particles. The water is also matter. So, and the matter particles are very tiny. You could not see water here, you could not see water here, not able to see water here. Just to show that property of a particle, that that the particles are always in continuous motion. Water particles are in motion. If you observe it, there are water particles also out here. These water particles are moving. So while they are moving, Sahasra is that pole, and there's a tuck kick. Another, she goes and she strikes against another water particle. Another water particle. They are all striking. Have you understood? So the third thing, these we will again come in kinetic theory of matter. These things we will be studying. 1, 2, 3. We also say particles of matter are in continuous motion. Have you understood? Particles of matter are in continuous motion. Is this thing clear? And this you could explain just by the illustration of the pollens in water. Can I rub this now and summarize what we have learned so far? Okay, I'm rubbing this part. Okay, let's see what we have learned. Hope it is not boring. Even if it is boring, you can't do anything. Studies are not a choice, but a compulsion. And the bigger compulsion in life is spending time with Mr. Jaideep Das. Don't scratch my car and do all those. He bores us so much. One day, one student asked me, "Sir, where do you park your car?" I said, "Why do you ask that question?" Immediately, I got a little bit worried. Nidhi must be thinking, any day when I come to board a car, I know she has seen where is my parking. I'll do. Okay, number one. Let's see the properties. Matter is composed of tiny particles. That's one property that we saw. Matter is composed of tiny particles. You can also go across, when you go to the channel and click on playlist, you will see CBSE grade 9. CBSE grade 9. Okay, you can watch that video also. Everything is same end of the day. Okay. So next one we said the particles have spaces in between them. And the third one we said the particles are in continuous new us motion. है ना ध्रुव, क्लियर है? तो मैटर इज कंपोज्ड ऑफ टाइनी पार्टिकल्स, KMnO4 example. Particles have space between them, both KMnO4 and sugar and water example. And particles are in continuous motion, pollen example, right? There is another property which did not come out evident in those particular illustration, but we'll discuss this also. The particles of matter attract each other. Now you will understand why I told you this story before learning the Cambridge part. Now things will fall easily. Particles of this matter attract each other, right? Have you understood? So let's see the illustration of everything. So this is a piece of matter, and more drawings, the more clarity you get. Okay. Now when you're observing it microscopically, this is microscope view. If you see microscope view, then the things that we will see are that this much portion, we are seeing this much portion, so they have particles. Understood? Let us call this particle 1, 2, 3, 4, 5, 7, 8, 6, 9. Clear, bacha? Now, matter is composed of tiny particles. These are the tiny particles. This is the microscopic view that you are getting. And if you want to draw your view, I'm always interested in drawing. I love drawing. So you can make an eye like this, and this is how you are seeing. Your eye is seeing this. Okay. Now, particles have spaces in between them. Please keep this concept very clear. This is something which is the space. Now these particles which we are talking about, later on when we go to kinetic theory of matter, we will understand these particles are nothing but atoms or molecules. But as of now, we will restrict to calling them as particles. So when we go to this chapter and talk about atoms and molecules, then this space we will be calling as intermolecular space. A space between two molecules, inter-school competition, a competition between schools, a space between molecules. So it's known as intermolecular space. Understood? Then we said the particles are in continuous motion. So these will also be in motion. You'll always see this motion means there will be a random vibration of these particles. Means the particles are always they're vibrating about the space. There's some random motion. Okay, there's some random motion. What is important for you now to understand is the particles of matter attract each other. So let's show that illustration, how the particles of matter attract each other. So I'm taking particle number 5 just for understanding. 5 will be attracting towards it, 5 will also get attracted, 5 will get attracted towards 3, will also attract, 5 will get attracted towards 9, will also attract. Are you understanding? There will be, and this will happen across all particles. This particular thing, when we study kinetic energy, kinetic theory of matter, we will call this as intermolecular force of attraction. Intermolecular force of attraction. A force of attraction which exists between two molecules. This is that force due to which if I am one molecule and Sahasra is one molecule, we are able to maintain our position. Understand, Sahasra? You are pulling me, I am also pulling you, and equivalently somebody is also pulling me this side, somebody is pulling me this side. So some equilibrium positions all of us have got. Otherwise, if you pull me, then we should come and collide with each other. So you are being pulled from the back here. So you have an equilibrium position, I have an equilibrium position. These two concepts will be very important. And if you understand the relation between these two, the chapter is a cakewalk. Now just understand. If two particles are very close to each other, that means there is more attraction. Universal law. I do not like somebody. So will I be close to that person or that thing? For example, I don't like bitter gourd. No matter how much my mother feeds me, bitter gourd to me looks like a crocodile. Have you seen bitter gourd? You cut it in a horizontal manner and put it on water, it assumes as if some crocodile is floating on water. So I don't have an attraction to it. You won't see bitter gourd close to me. So if the intermolecular space is less, what do you understand about the intermolecular force of attraction? More. So can I write that the intermolecular force of attraction is a quantity which is inversely related to the intermolecular space? Do you understand this thing? Do you understand this mathematics? Inverse relation means if you increase this, this is gonna reduce. If you reduce this, this is gonna increase. Nowadays we are no more friends. I am no more friends with Kirtan. So my attraction to Kirtan has reduced. Your attraction, so our spacing will increase. Kirtan and me are seen very close to each other. The attraction is more between us. So keep this in mind. Okay. And let's talk about the particles of matter attract each other. Let's try to understand this concept also. Let me say that this is a bar of the dairy milk, whatever it is, silky or bubbly, whatever you take, the fat bar. Got it? And refrigerate it properly. Make it hard. And imagine that this dairy milk is just like a flat slab. Generally, dairy milk have got cubes and perforations on it, so it becomes easy for you to break. But suppose there is no perforations or any marking or anything, it's a flat slab, just like this tabletop, okay? And I have refrigerated it in such a manner, ekdam tight hai. Means if you take it and throw it on Dhruv, his head will have injured by dairy milk, okay? You try to break it now. No matter how much you think you will be breaking it in a straight line, don't you think the way it will break will something like this? This happens in chocolate, all of us. Don't try this with 5-star because that is all me. Try this with only dairy milk and other things. Okay, it will break in this manner. Agreed? So let's try to see what is happening here. If you try to see this portion also in a magnified manner, So this portion had dairy milk particles, particle, and our friend Kirtan was thinking that he would be able to perforate it or break it exactly in such a manner that all the four particles will be apart. Now we are thinking microscopically, okay, but there are particles on this side also. So these other particles are holding them. Don't go, don't go. No, your Kirtan is pulling me. No, don't go, don't go. Somewhere something happened that instead of all the particles going away, one or two particles did not go away, and as such, the cut that you get, you're getting it as a corner formation. Are you getting it? An edge, extra edge has come out. When I was a kid, somebody used to give me a chocolate and broken piece. I used to say, no, this is discarded. Why? Edge has come out. Extra corner has come out. Chocolate is supposed to be only four corners. Now, if you break it in that way, it becomes a trapezium. So you'll get one more corner. So have you understood? This clearly shows that particles of matter attract each other. Now, imagine the condition that I had put to you. The condition was refrigerate this dairy milk before performing it. Why did you refrigerate it? Because you wanted to make it dead rock hard solid. What were you playing on? You were playing on the policy, on the principle that if you refrigerate it properly, these particles will come close to each other, right? And the force of attraction will be very high. Try to do the same thing with a piece of bread. Happily, it will break into straight line. Because the forces of attraction are not strong. So do you understand that there is a force of attraction between the particles? This is an illustration to show you this. These four things, keep it kindly in your head. This is end of part A of our today's discussion. Have you understood? We spoke about matter, we spoke about particles of matter, and we understood four things about particles of matter. They are tiny particles, and these tiny particles in our later section we'll study them as atoms and molecules. They got spaces between them, which we'll be calling as intermolecular space. They have attraction between them, which we call as intermolecular force of attraction, and they're always in continuous motion. Right? When you were heating that cup of sugar solution, you were actually imparting more energy. More energy. Think about a child in PBL city who is very, hyperactive, lot of energy, and you go and give him, yo, beta, good, excellent. You pep him up with more energy. What will happen? It will vibrate more. So these particles of water were vibrating. You put it inside a microwave, imparting more energy. More energy means more less. You know one thing, the more energy you have, the less is the stability. Sir, I didn't understand you. Okay, let's take an example. Suppose you have a younger brother or a younger sister at home, and that one is absolutely like, till he or she is awake, the whole house is a mess. That means we say what? The child is very energetic, whole day hyperactive. But when you go and observe the child when the child is sleeping. All energy gone, system is more stable. So if you give more energy, you are making it more unstable. So they widen up. And as soon as they widen up, they say, sugar, come here, come and occupy the space. So the solubility increases. Any questions on this, you can ask. No questions means two things. Either you have understood everything, in which case I am very happy, or you have not understood anything, or the third one, there is some bit of doubt, but you feel ashamed to ask. I have a problem only on the third condition. Never have any sort of fear factor to ask, because these things are not grandma stories. We learn it more better when we participate. Otherwise, it becomes a monologue. You know what is monologue? I keep on speaking. So just imagine, before you, there was one batch whom I narrated the same story. To you, I am narrating the same story. So you should be also empathetic to me to bring in some discussion so that it remains lively. Okay, that's how we learn. This much have you understood? Let's go to the next section. Okay, so we know intermolecular force of attraction is inversely proportional to intermolecular space. Can I rub this, children, now? Very good. Now, as we have now talking about matter, now we get deep inside again the Cambridge story. So we talk about something known as the states of matter. And the states of matter are predominantly solid, liquid, and gases, or gas. If we've used a plural singular everywhere, we'll use a singular here also. One of the things, please understand that you can always convert one form to the other. Interconversion is possible. Is possible, and you do this by by adjusting two parameters, precisely pressure and temperature. Sir, I did not understand whatever you told. Ice, solid. Start heating it, liquid. Start heating it, changes to steam. Cool the steam, condenses to liquid. Cool the liquid further, freezes to ice. Understood? That, sir, you told about temperature. Can you tell us about pressure? Okay. Now, out in Pebble City, you see the gas coming in pipe, but before that, if you go to your relatives in some houses, you'll see red color cylinder. So the cylinder, right? You use cylinder at home? No, but you must be seeing in somebody's houses cylinders are being used. So inside the cylinder, what is it? Liquefied petroleum gas. The gas is in liquid because it is pressurized. Why should I talk about cylinder? Let us talk about deo spray. Every one of us uses. So if you see a deo spray has got liquid inside it, but the liquid has been pressurized and kept inside. When you spray, what are you doing actually? Try to understand. What are you doing? You are actually, see, a deo spray is something like this. This is a deo spray can, and there is a choke valve out here. This is the inside of the can, okay? And to this, you are actually applying pressure with your thumb. And this is highly pressurized. It is in liquid. As soon as you press it, this orifice opens up, and the pressure outside is much less. So you are reducing the pressure, you are releasing the pressure. So when in LPG we release the pressure, the liquid immediately converts into gas. Have you seen lighters? Many people use cigarette lighters or gas lighters which have got liquid inside it, and when they just strike it up, the flame comes out. How is the flame coming out? Inside you have got liquid, but as soon as the liquid comes outside means it comes to the, it's exposed to outside, it immediately loses its pressure, and once you lose its pressure, you change your form from liquid to gas. That is a way in which we can actually send more gas to you. So your question should be, sir, why did they not fill gas into our red cylinders? If they fill gas in your red cylinders, they won't be able to ship more gas to you. The cylinder itself is heavy. So what did I do? I converted that gas into a liquid form by compressing it and then sent it to her house. Whenever she uses, this much of liquid comes out and this much of gas is formed. So won't you be able to use it more? Yes. Nowadays there are some packing materials. Suppose you're going for an international trip and you have a lot of, there is a lot of space that these garments occupy within them. So what they have got some evacuation bags. So you are supposed to put your garments in a bag, connect it with a pump, and they'll just suck out everything, and your all clothes will just become popper-like structures, right? And you will be able to take more and more volume of clothes. Immediately when you unzip your bag, it will fluff out. The same thing, right? So interconversion is always possible, and this interconversion is possible. We actually play between two parameters, one is pressure and one is temperature. By playing between these two parameters, that's why. So the question may come to you, how can you change states of matter? We can change states of matter either by changing the pressure or the temperature, or by a combination of both. That we will see. Like if you increase, what happens? If you decrease, what happens? Is this much understood to you? Okay. At this juncture, we will also discuss about two more things called rigid versus fluid. What does it come to your mind when we talk about rigid and fluid? Rigid is, he is very rigid in his decision. What do we say the opposite? He is very, what is the English that we use? Sahasra is a very rigid in her decision. You don't like rigid teachers. So what is the opposite? Come on, you're learning in Cambridge. How can you be short of words? Flexible. But in chemistry, we use the word fluid. Fluid means anything that can flow. Anything that can flow. Ice cream, the ice cream has just melted, so the ice cream can flow. Heat is called a fluid. So heat fluid, yeah, we can't see heat, but if you start heating this part, this zone also gets heated. So heat flows. Therefore, heat is fluidic in nature. Rigid means rigid. You know what is rigid? Rigid means this board will be considered. If you want the exact definition of rigid as per physics, the exact definition of rigid is take a piece of matter and let's say point out 2 points in that A and B and subject this piece of matter to external forces. The distance between A and B should not change, and when you relieve it from the forces, then also it should not change. Then we call it rigid. See the difference between grade 8 and grade 9. At grade 8, the things that you were studying, you were not studying at this deeper level. From 9 onwards, you have to study science with a deeper level. Question: why is the cushion not rigid? When I apply a force on the cushion by sitting, 2 points in the cushion come close to each other. And when I relieve myself and get off from the cushion, the 2 points again get separated from each other. But if you are rigid, let's say a railway track, and our friend Kirtan is already very thin. He goes and stands on it. Do you expect 2 points on the railway track to contract? And even if he gets off it, do you expect them to expand? No. The railway track is rigid. But in physics, we say nothing is 100% rigid. We only assume anything to be a rigid body. You feel that this piece of plywood is very rigid because even if I push it, it doesn't. No, it is not rigid. It's not rigid. Some compression is happening. High speed photography will show you. Actually, they show like a cricket bat when it is hitting a six. The ball actually, the shape of the ball changes when it comes in contact at collision. The bat shape. Again, they regain their shape. By high speed photography, it can be shown that nothing is permanently rigid. Now, this is one parameter which will help us a lot to distinguish between solid, liquid, and gases. You yourself try to say who has more rigid tendency? Solids. Liquids have less rigid tendency. So, let us try to bring out some common points of difference between them. Can we, from our basic knowledge, tell me how do you differentiate between solid, liquid, and gases? But before that, we'll say solids have definite shape. Don't you agree? And a definite volume. A dairy milk has a definite volume and a definite shape. What would you say for liquid? I take out all your water and pour in her bottle, it will take the shape of her bottle. Liquids do not have definite shape, but they have definite volume. If it is half liter water in your bottle, even if I pour it in her bottle, it will be half liter only, but the shape will be her bottle shape. Do you get it? So liquids have definite volume. What about gas? Neither definite volume nor shape. Do you think gases have got a definite shape and definite volume? No. You enclose gas in a container, it takes the space of the container. You enclose gas in a what you call a room, it will take the shape of the room. Agreed? Then can we talk about something called density? Do you know what is density? Density is mass upon volume. Density, if something has, okay, what do you exactly understand by density? What? Okay, tell me, what is more heavy, 1 kilo iron or 1 kilo feather? They are equal. Then what is the difference? 1 kilo iron I can just steal in my pocket. To bring 1 kilo feather, I have to be like a Santa Claus. Volume. So solids have more density. You can take a potato like this. Same mass, if you want to take milk, you have to take it in a tumbler. And gas means they have no density at all. So in terms of density, if we talk in terms of density, then you find the density is highest. This is less than solids, and here it will be least. Again, you should remember mercury is an element, metal, which is liquid at room temperature. Okay, getting boring or what? No? Okay, density. After density, let's talk about something called compressibility. 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 Tell me about compressibility. This is all talking about rigid and fluid. Can you compress solids? No, you can. You can. But in solids, it will be very less. Very less. Liquids, can you compress liquids? No, you can't compress liquids also. Means you can compress it if you apply pressure and temperature, otherwise liquid. So just think yourself, take some water in a syringe, you know syringe, and put your finger on the tip of the syringe without the needle and try pushing the piston. Will you be able to press it? No. So liquids are also very less, very less. But here you can, compressibility is very high. Compressibility is very high. Are we fine on this? One, we spoke about shape. So these have got a definite shape and a definite volume. The other one has definite volume. The other one has neither definite shape nor definite volume. Liquids, what do we say about shape? Liquids tend to take the shape of the object in which they are kept. If you put milk in a bottle, it looks like a bottle of milk. If you put milk in a vessel, it looks like a vessel full with milk. Okay, understood? Compressibility, solids and liquids cannot be compressed. Maybe it's marginal. Whereas if you take about gases, gases can be compressed a lot. Just imagine when you inflate your car tire, what are you doing? You're taking a cylinder and there's a piston, and the piston goes and compresses the air. And then it releases. Understood? Right. And so we spoke about compressibility. Anything else that you find? How would you like to deal on these two properties? These two properties. Intermolecular force of attraction. How would you like to say? So we took, this was one property, density was second, compressibility was third. Let's take the fourth property as intermolecular force of attraction. Where do you think the force of attraction is more? In solids, definitely, very good. Here we will find it is the highest. Here it is somewhat. And here the intermolecular force of attraction will be least. And how about, my dear children, on intermolecular space? Tell me on intermolecular space. Gas, the intermolecular space will be the highest. Excellent, Dhruv. This will be the highest. Here it will be mediocre, and here it will be the least. Now put yourself into the questions. The fluidic nature or the compressibility directly depends upon the intermolecular space. More is the space, more you can compress. Children are seated like king. They are seated only 3 children in one seat. The conductor says compress. And if the children are 5 children already in the seat, you can't compress anymore. Does it make sense? Compressibility. Okay. So I'm just seeing, we understand what is matter, we understand what is fluid, we understand what is stature, and since this is theory, we won't go any further, because if you go further, then you'll start getting bored up. Have you understood this much or not? Tell me. Clear? Anything here that you would like? Next class, we will be discussing about these conversions. What are the names of these conversions, which you obviously by now might be knowing: melting, evaporation, freezing, boiling, condensation. But we will see them more detailed. What is melting? When does melting happen? What are the conditions for melting? Chemistry, we have to be, it's theory, so we can't help it. And preferably before coming to the class, have some citrus drink and come. This will keep you more alive. I see a little bit dip in energy level as compared to yesterday. Or else, another thing I'll tell you, the day you go for playing or something, this particular tuition day, please don't go to play before you come. Not because I don't want you to play, you will get exhausted. Because in playing, you move a lot. And then suddenly here you will come and you are not allowed to move for 1 hour. So slowly sleep factor will come. Rather, you finish some school homeworks when your school will be there, and try to have some health drink, whether you are having Bonvita or something, some juice, so that you are able to keep yourself alive. Or if you are bringing water, go and buy 1 pack of Glucon-D from Ratnadeep, and mix that glucon D. Glucose gives you instant energy. Because children, whether we like or not, I am at least trying to make so much of diagrams. I can assure you, not boasting, your school, nobody will draw so many diagrams on board. They'll show it to you in PowerPoint, PPT, tick, 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 or they'll give you a research project. That is the best way. Easy job for me, but I want you to get interested in this. So much of writing. Every class I am filling ink. I just got 3 more bottles of ink. Right? The idea is that you should fall in love. And if you think that something more I can do to make it interesting, I'll make it more interesting. Actually, in your batches, we don't have students who bring out class discussion. Like in the CBSE grade 9 batch, a lot of their discussion, you know what happened in class today, sir? This one got scolding, that one. So those talks come up, children remain pepped up. So please, don't be quiet. Slowly we'll mix up. चुप रहने से आप भी सो जाओगे, मैं भी सो जाऊंगा. ऐसा नहीं हो सकता है. ठीक है? Okay, Nidhi, what you have been waiting for? The clock strikes 8 and now all the mice get turned into horses and the pumpkin becomes a carriage. Cinderella is out of the class now. Right? Bye-bye and see you tomorrow, not tomorrow, on Sunday with mathematics. Until then, throw rotten tomatoes on my channel and please put the dislike button, but please do study. And today the voice is recorded. Bye.